Today we are discussing how ancient microbes can reduce gas bills and carbon dioxide. And we are here with Dr. Alexander Krajete, founder and chief executive officer of the Austrian company Krajete GmbH. Hi, Alexander. Good afternoon from London. How are you?
I'm fine, thank you. Good afternoon.
So today we are discussing about biological gas production because we know that your company has an expertise in this kind of area and purification. And we want to learn more about the process of the company, which is based on microorganisms, that this process allows the highly efficient and environmentally friendly conversion of climate damaging carbon dioxide and hydrogen into storable methane. Can you tell us a little bit more about the technology?
Yes, absolutely. It's an ancient technology, basically fostered around the oldest metabolism on Earth. This metabolism is called methanogenesis, and it's the metabolism of so-called archaea microorganisms. They are around 4 billion years old, and they originated in times when oxygen did not exist, when more or less energy was derived based on redox processes using CO2 and hydrogen, yielding methane as a product. And that's something we started to work on already 10 years ago. It's a biotechnological process using ancient microbes, which have, as mentioned, this intrinsic ability to convert carbon dioxide and hydrogen, producing methane or a hydrocarbon as an energy carrier, basically, and therefore not only reducing the carbon dioxide amount, but also allowing to store renewable electricity in the form of hydrogen by producing methane as the main constituent of natural gas. That is it in essence. So it's a natural process, 4 billion years old, not really used industrially, but discovered not only by us, but more or less driven towards engineering and upscaling for industrial applications. And there is now some interesting novel applications around this process.
As you mentioned, this group of microorganisms have existed on Earth for billions of years and are now found in particular where extreme temperatures or pressure prevail. Can you tell us how your company managed to tame these microbes for natural gas production?
That's a very valid and interesting question. It's very simple. My educational background is a chemical one. I'm an industrial chemist, and I've ever since worked with pressures and temperatures, basically in industrial environments that allow the treatment of especially chemical catalysts under harsh conditions. And now that we have discovered the potential of archaea microorganisms, the challenge was to take them out of a natural living environment, bring them into a chemical reactor, and tame them, as you have mentioned, by exposing to conditions which they need, pressures or temperatures or both, depending on what the requirements are. So we do have the technical ability to grow those microbes under either high temperature or high pressure conditions or both. They do belong in a way to extremophiles because they are different to normal microbes, because normal microbes, they would die at higher temperatures or pressures. But those archaea microorganisms are more or less survivors of nature. As mentioned, 4 billion years old, they used to dominate the Earth surface, but from the moment oxygen started to kick in with photosynthesis, and oxygen is a poison for them, they more or less retreated into environments deprived of oxygen, and that's the reason why you find them in volcanoes, at deep sea vents at the bottom of the ocean. You find them in soil and everywhere in the absence of oxygen. So we are more or less transferring chemical organometallic conditions, which are equally free of air and oxygen, to a bioreactor by applying also pressures and temperatures, and more or less transferring the knowledge of chemistry and chemical engineering to biology or microbiology. And by combining two opposite disciplines, we are creating here a novel field of high pressure biotechnology, which is more or less the source of everything which is linked to gas fermentation, perhaps giving access to new green chemicals as well, which are made in a totally original way or novel way.
So, if I understand well, probably your technology creates the environment that the microbes want to survive. And later on, you use the existence of the microbes to convert them into methane. Is that correct?
Yeah, that's correct. Yeah, that is it. In essence, we are not only growing those microbes under conditions that are extreme from a biological point of view, not from a chemical one, but we are able to keep them, to maintain their metabolism, to speed it up, because that's what matters very much in chemical engineering, to have high space time yields. And that's also one of the reasons why often biotechnological processes are not prevalent. They are often slow, but we manage to combine specificity with high turnovers and high production yields. And that's in a way the exclusive knowledge and technology which we have developed that allows us to access a completely novel pool of biocatalysts, being living microorganisms with the intrinsic ability to not only create methane, but also inter and intracellular compartments, which could maybe one day also serve pharmacy as a lead component or lead target molecules for completely novel applications. Not discovered at all, but I think it's the starting point of a completely new discipline with potentially a revolutionary character.
Can you tell us a little bit more about the role of these microbes in converting carbon dioxide and hydrogen into methane? What's the role in this process of these microbes?
The microbes, they can't avoid producing methane. Basically, if you draw analogies to plants or to humans, to animals, to photosynthesis or respiration, you would have the same analogy. Just as a plant cannot avoid producing oxygen because it's meant to use carbon dioxide and water, and we humans doing the opposite, breathing, we can't avoid producing CO2. Those microbes have a redox-based process at the basis of their life, their metabolism, and they simply need to convert those two gases, CO2 and hydrogen, with methane being the byproduct. That's the interesting thing about it. We are basically using their byproduct of their metabolism, their life, which serves basically as an energy carrier for us humans, because methane is, as we all know, the main constituent of natural gas, which can be used for everything you can imagine, from producing electricity to mechanical energy, to heat, to all forms of energy that can be derived from methane. So it's a very interesting approach. It's just that those microbes haven't been popular until now, because as said, first microbiologists need to find them, to characterize, to name them, to give them way to textbooks, to biology. Then afterwards, engineering comes, applications and economy at the end of the value chain. So I think there is hidden potential in an own life domain, and we have three of them, and they constitute on basically this. When you categorize organisms, they belong to an own domain, more or less, whose potential was not discovered until now.
Can you tell us how easy it is for anyone to produce gas in their own backyard and cut dependence on imported gas? Because as I can understand, the technology offers a solution that gives the chance to every household to produce their gas that they might need during their day. So can you tell us a little bit more about how this technology works in terms of when it's applied in a typical household?
Basically, we are now spanning a big leap from the original development in a high-pressure biotechnology reactor, which no one wanted, because it requires pressures and lots of technical sophistication without any chance to enter a household. So we have more or less downscaled and simplified this high-tech biotechnology to something simple that is compatible with household applications by having more or less a miniaturized home biogas plant filled with manure for activating more or less the broth, the liquid. Then kitchen waste is added to those home fermenters with a total volume of around 1,000 liters. And then this whole process of fermentation and degrading biomass to biogas, which is a mix of natural gas and CO2, starts by itself. Once you have the temperature It does not require pressure. And you continuously feed this home biogas fermenter with kitchen waste on a daily basis, more or less, by producing biogas. And now you would, of course, like to upgrade the biogas to natural gas because biogas is only 50% methane, while natural gas is 100% methane. You accomplish it by applying one of three steps or three steps in a consecutive order. First, we are adding bio booster. That's specific methanogenic microorganisms that serve as a sprinter in the biodegrading process. They are more or less facilitating the methane generation and therefore increasing the methane content from 50 to around 60 or 70%. That's the first measure. The second measure is to apply hydrogen, and that hydrogen can be of green origin with water at its basis and renewable electricity. So by coupling a photovoltaic solar panel with an electrolyzer, you can produce hydrogen, store it in bottle, and use that hydrogen to bubble it through this home fermenter. By doing this, you are giving microbes the chance to perform methanogenesis and produce even more methane. Therefore, the methane content increases to around 80%, and the fine polishing to reach the purity and quality level of the natural gas grid is accomplished by employing a so-called adsorber. That's basically a separation method which is linked to special zeolite spherical particles that are able to selectively trap the remaining CO2 in this enriched biogas. And by separating the CO2 out of those 80% methane I mentioned, we are generating 95% methane plus, which is more or less the equivalent of the imported fossil natural gas, which is coming from fossil-rich countries. So it's a completely different way to generate natural gas from different ingredients, combining different methods. As you see, you have the kitchen waste as the resource. This is yielding half natural gas, half CO2. Then by applying the principle of bio-boosting, adding a bit of hydrogen, and ultimately taking and removing the CO2 fraction with adsorption, or by combining biological and chemical methods and means, a household could be basically autonomous and generate its own natural gas. That's a completely different approach. So basically, it's the question geopolitics or bio high tech. We are advocates of the second option. We strongly believe that science and technology can pave the way to totally different ways of harnessing energy.
I'm wondering if you have estimated how much kitchen waste is needed to produce enough biogas to power a home during a day. And the second question is, how costly, how expensive is this process technology for a typical homeowner to apply it in his home?
Yeah, to give you a comparison of numbers, I mean, 1 ton of kitchen waste can yield around 1,000 kilowatt hours of thermal energy equivalents in form of methane. That's around 100 cubic meter of natural gas. Now, I don't know how much is used to heat a home or an apartment, depends on the insulation and the size of the heated area. But those 70, 80 kilograms of natural gas, they can last for, depending again also on the country and the area you want to heat, for sure for a couple of weeks. That's one thing. So the stuff we are throwing away into those bio garbages and bio cans is basically a resource for generating natural gas as a substituent, which would especially serve the purpose to cover the energy gaps in the winter, because usually we have surpluses in summer, but not enough energy in the winter. As for cost, since this is a prototype, a completely novel development, at the moment, the cost of all ingredients is in the range of 10,000 euro. But once a market opens up and we see there is interest, for sure, this can be further improved, and I think the target cost could be even something between 3,000 and 5,000 euro once, as I mentioned, the market opens and there is interest for this technology.